Now we're going to look at some examples of frequency modulation and listen to what it sounds like, and then we're going to look at the theory and the principles behind these sounds and try to understand how they work. So we're going to be looking at some code called code4.sal. You can download and study the code, run it, change it, and work with it yourself. I'm going to switch over to Nyquist where I have code 4 loaded up. And we're going to start by evaluating the first expression, which I'm going to do by highlighting the expression, selecting the expression, and typing Command U. That way we can evaluate these expressions one at a time. Okay, so that's FM OSC with the pitch of E5 and a low frequency oscillator. You can see over here that we've multiplied by 20, which gives us a 20 plus and minus 20 hertz frequency deviation in E5. And we're using a fairly obnoxious bright saw table as the waveform. Okay, next I'm going to do the same thing but change the pitch to E3. And you might notice that the frequency deviation sounds even more extreme, even though it's the same value of 20 hertz. And that's because our perception of pitch is more based on ratios than absolute frequency deviation. And so one way to deal with that or to model that is we can define functions where the frequency deviation is proportional to the fundamental frequency of the pitch. And that's what we've done in this function VibTone. The crucial part is right here, I'll highlight it, where we take the pitch that we're using, convert it from steps to hertz, so that gives us frequency, and then we're scaling whatever the amplitude, whatever the frequency modulation function is, it gets scaled by pitch. So as the pitch goes down, the vibrato is lower. And then we're scaling that by a vibamp parameter 0.01, which is just scaling, and multiplying that by LFO of 6, which actually generates the vibrato. So now if we play VibTone of either E5 or E3 pitch, it should sound perceptually more or less the same quality of vibrato, same depth. And then lower. Okay, so more equal sounding vibrato. The next thing we're going to look at is adding some functions to change the rate of vibrato. And we're going to, if you want to change the, have the vibrato change frequency, this is sort of a nested frequency modulation, because we're modulating the vibrato frequency, and we're then using the vibrato to modulate the fundamental frequency of a tone. So here is the Hertz OSC, where we're passing in the frequency parameter to generate vibrato. And where does that frequency parameter come from? Well, here's the expression. It's PWLV, which, so let me interpret this for you. We start at amplitude of 1, and after 1 unit of time, we increase to 10. So this will be increasing depth of vibrato. This whole thing is getting stretched by 2, so it'll have a duration of 2. And let's listen to that. Okay, so you hear the vibrato speeding up. If that sounds a little noisy to you, in addition, that's actually aliasing that we're hearing because of the use of this saw table. But that's a different story. Let's move on. All right, so one of the reasons that we are interested in FM synthesis is it helps us to generate some very interesting, rich, complex tones. And so I put some code in here, which is not FM synthesis, just to illustrate the idea of complex tones that change over time, done in a constructive way, putting sinusoids together so that you can see what that looks like. So in this expression, let's see, we are simultaneous. That's what SimRep is, a simultaneous repetition. We're making 20 copies of something, and the something is Hertz-Osk, which is a sinusoid, with a frequency of, fundamental frequency of C3, but we're multiplying by I plus 1, so we're actually generating harmonics or multiples of that C3 tone, and we're multiplying everything by a piecewise exponential function that causes it to decay, and we're stretching by 6. Okay, so just summing up a bunch of exponentially decaying harmonics. And we hear that exponential decay. We hear a fairly rich sound because we're adding 20 sinusoids together. But that's a fair amount of work. We're adding up 20 different oscillators. Another way to get that kind of changing quality of and richness of sound is to use filters. And so here's some code. I'm just going to execute this first. We'll listen to it. Okay, so you hear that sound quality sort of changing over time, and that's because we're applying a filter to a fairly bright wavetable sound. Actually, we're using buzz, which generates 20 harmonics, but those are filtered. Okay, so we'll come back to comparing frequency modulation sounds to other synthesis techniques. All right, so let's take our FM LFO function, modulation function, and let's take the vibrato rate from 3 all the way up to 100, just for fun, to hear what a very high vibrato rate sounds like. Okay, so you can hear, especially at the end there, that something very strange is happening, that we lose the sense of what we would call vibrato or some wavering in the tone or in the pitch. And in fact, what starts happening are changes in the tonal quality of the sound. And that is really the basis for FM. We're going to try to understand this more theoretically later. But let's go even further now, and we'll take the modulation. Sorry. So now what we're going to do is start with a very low amount of vibrato and increase that vibrato up to a large, wide vibrato, but we're going to do it at a kind of a normal, slow 6 Hertz rate. Okay, so it sounds kind of silly, but you understand what's happening. You can follow what's happening there. Now what we're going to do is increase the vibrato rate. So the vibrato rate now is 500. So if the amplitude of the vibrato is very low, like 1 Hertz, you don't really expect it to have much effect. Imagine if it was 0 Hertz, there'd be no effect at all, and we'd get a sinusoid out. But as we increase the amount of the depth of vibrato, the, the amount by which the modulated signal goes up in frequency and down in frequency. As we increase that, well, listen to what happens. So you hear some kind of strange tonal qualities, and it's actually getting brighter over time. So typically, when we do FM synthesis, and we'll learn more about this later, typically we use integer-related modulation at a fixed frequency. So that's what we're going to do here. We're using the FMOSC function, and we're going to modulate. We're going to take a C4 as the fundamental frequency of this tone, and we're going to modulate it with a modulator that's also C4. So it's a 1-to-1 frequency ratio. And we're increasing the depth of modulation from 1 hertz up to 4,000 hertz. Huge frequency deviation. And let's listen. Okay, so that evolution of sound is a very characteristic FM synthesis sound. It's one of the interesting things about FM synthesis is you can generate these very complex evolving sounds by very simple means, just 2 oscillators and a few parameters. The fact that it is a little bit characteristic is one of the drawbacks of FM synthesis, that people tend to recognize, oh, that's FM synthesis. Okay, so let's stop here. This might be a good time for you to take a break and download this code4.sal, go through it, read the comments, play with it, make sure you understand what's going on. And we are now going to continue talking about the theory behind all of this and what makes it work. So first of all, why FM synthesis? Well, we've already seen wavetable and table lookup synthesis. I can tell you that that's a very efficient way to make sounds. You can create really any harmonic spectrum by just loading it into a table and playing it. And you have very simple frequency control and amplitude control. So wavetable synthesis or table lookup oscillators is a very practical, reasonable thing to do, but there's something missing, and that is time varying control over the spectrum of the sound. If you're doing table lookup, you have a fixed table, and so the wave shape that you generate out of this table, even if you speed it up or you make it bigger, higher amplitude, it's always going to be the same shape, and your ears pick that up. It's actually a somewhat uncharacteristic property to have this invariant wave shape in the face of changing frequency and amplitude. The other problem with table lookup is that there's no direct way to create inharmonic spectra. We've learned that if you have a periodic signal, you have harmonically spaced spectra. So if you want to make some of those dissonant or metallic or unpitched sounds, you're not going to do that well with table lookup oscillators. You can, of course, add lots of them together and introduce inharmonic partials, but then you're doing a lot more computation. So that's one approach. Synthesize each sinusoid separately. It's tedious to control. It's costly. You can filter the output of the table, and we saw an example of that. And that's useful, but restricts you to harmonic output, and sometimes it's hard to design and control filters to create a wide variety of sounds. And then another approach is FM synthesis. So let's look at what happens during FM frequency modulation in terms of the frequency domain. So we know that with low frequency modulation, such as vibrato, what's happening is the entire spectrum is just moving up and down, higher frequency, lower frequency. no big surprise there. But when you start to modulate a signal and the modulation is in the audio range, then some very interesting things happen. And this is a picture. So we're going to take this initial sinusoidal frequency represented by this impulse. All right, and this is, we're in the frequency domain, so this is the frequency axis is horizontal, and the amplitude or energy is the vertical axis. And this is a very qualitative picture. But what happens is, starting with this single frequency, this single sinusoid, when I modulate that frequency at audio rates, then what happens is what are called sidebands are generated. There's a lower frequency here and an even lower frequency here. There's a higher frequency and an even higher frequency. The separation between these new frequencies that are generated, the separation is the modulation frequency. So if I modulate by 100 hertz, then I get a separation of 100 hertz, regardless of where the thing being modulated is. This thing being modulated, by the way, once again is called the carrier. So we get the carrier frequency plus and minus multiples of the modulation frequency. And now the question is, so how big are these sidebands, and how many are there? Well, it varies. It varies with the mainly with the depth of modulation. So the greater the depth, in other words, in the time domain, the greater the frequency variation of this carrier frequency, then in the frequency domain, the stronger are these side partials. Now, this is almost magical. It's somewhat counterintuitive that in the computationally, what we're doing is we're taking this carrier frequency and we're moving it down and moving it up and moving it down. So you'd sort of expect it to, the resulting spectrum to be this smeared out cloud of frequencies around the carrier frequency. But that's not what happens. In fact, these very regularly spaced new sinusoidal components are added. And that's what makes FM synthesis so interesting and valuable. So there's a little more math on this slide. Let's read this note here, that the number of significant partials is roughly the ratio of the modulation amplitude. So in other words, the frequency deviation, the ratio of that to the modulation frequency. So that's a formula that can help you estimate what the depth of modulation should be for some given effect. Now, that's a qualitative description. What about the precise formula for what happens when you do FM synthesis? Well, I'm not going to give you the exact formula. It's because it's messy. The exact amplitudes of the partials that are generated by FM are described by Bessel functions. You can look up Bessel functions. They're interesting looking, and you could say they're messy. The evolution of Bessel functions, in other words, as you increase the depth of modulation, these Bessel functions are parameterized, and so they change, and the evolution is even messier. And most importantly, that there's no simple way to invert these functions. So if I were to say I want to recreate a trumpet sound, and I'm going to analyze the trumpet and measure the evolution of all the partials of the trumpet, and now I'm just going to look for FM parameters that reproduce that. That's what I mean by inverting these functions. We want to go from the result, the spectrum that we want, back into the control parameters. You can't, there's no general method for doing that. So FM has had many lives throughout over the course of almost 50 years. In 1967 to 1968, FM was FM synthesis was invented by John Chowning. He patented this in 1975. It was a very important patent for John and for Stanford University and for computer music at Stanford. It was licensed by Yamaha, and in 1983 they came out with the DX7 synthesizer. They sold 160,000, which was a very large number, millions and millions of dollars. So it was a very important product. In the years after that, new synthesis techniques came along, sample-based synthesizers came along, and FM sort of receded a little bit. But in the 90s, IBM PC-compatible sound cards came out, and because of the low cost of FM, a lot of these sound cards supported FM synthesis, and it once again became very popular in video games and all sorts of applications. And then once again, in the 2000s, after FM had sort of disappeared, cell phones with ringtones were introduced, and once again, FM and its very low computational cost enabled some fairly powerful synthesis to be added into cell phones. And this was just before large memory became available, which once again sort of wiped out the use of FM synthesis, because now you just put MP3 encoded audio and use that for ringtones, and people are happy with that.